So good morning. Today's lesson, I get quite excited about this topic because we introduce how CPUs work, what's inside a CPU, and how they actually process data. So at the start of each topic, we rate our confidence to find out how much we know already so we can pitch the lessons appropriately. So can you get logged onto the BLE for me, please? And click on Half Term 3, Computers 1, and rate your confidence on each of these learning objectives. So there's only two, but they're both jam-packed full of quite a lot of stuff. The first one, 3.1.1, just talks about the von Neumann processor architecture, and there's a lot involved in here. Remember, at the start of the topic, it's fine and it's expected for you to say that you're not that confident yet, because we'll rate our confidence again at the end of the topic and we can reflect and see how much progress we've made and what we still need to recover later on. Also in this topic, we're going to talk about secondary storage devices, and the three main types of secondary storage. So rate your confidence on each of those for me, please. Great, so we're looking at the stored program concept, the idea of how you can store a program in your hard disk, what happens to it to get it into RAM, and how the processor can understand that program to be able to do anything, to use Word, to use Google Chrome, to play the games that you do. We're going to look at von Neumann processor architecture, what that means. We're going to understand what makes one processor faster or slower than another one, and focus on each stage of the fetch, decode, execute cycle. So processors have been around for a long time. Digital computers are a relatively recent invention, but computers have been around for a long time. So way back in the 17th century, mathematicians came up with devices that could perform calculations with moving parts. So this is not a digital computer, but it is a mechanical computer. And you can go back thousands of years to the Antikythera mechanism that was used to calculate like the position of the sun, the moon, the stars, the planets for navigation purposes. So it's not a new thing to get machines to calculate stuff, but it is a really powerful thing to get digital electronics to calculate stuff reliably and quickly. So Alan Turing came up with the idea that you should be able to solve almost any problem with a universal computing machine. And so he came up with this idea of, wouldn't it be nice if instead of a machine that makes your cheese toasties or another machine that drives you from one place to another, what about if you had a machine that you could program to do anything, a general purpose computer, one that you can program, one that you can tell what to do. Originally, you program it with punched tape. So think of like masking tape, but with holes in. And where the holes are means what the computer has to do. So that idea evolved into a stored program idea. And John von Neumann, who was a brilliant polymath, which means he was like really good at all sorts of different things, published a paper about the idea of how you can store both data and instructions in a machine that would be able to solve almost any problem. And not all of, the vast majority of modern processors follow John von Neumann's model, which is what we're going to look at in this topic. So the idea is we have this arithmetic logic unit. So arithmetic you'll do in maths. Arithmetic logic unit is just something that does arithmetic, as in it can add, it can subtract, it can multiply, it can divide. Or logic, as in it can compare something and say something's bigger or something's smaller, or you can do and or a not. It basically does calculations. It reads stuff in from the outside world, it sends stuff out to the outside world, and it can store stuff. The stuff it can store is both instructions, that's your program, what to do, and your data, that's your variables, the high score in your game and the pixel data for Photoshop and that kind of stuff. So that leads us to fetch, decode, execute. Think of it like a dog being told to fetch a stick. On the stick is an instruction saying, run away because somebody's chasing you. And then execute means, I'll actually run away now. So fetch, decode, execute is all that a CPU does. People think that CPUs are magic. There's no magic involved. They just do three things over and over and over and over again. Those three things are fetch an instruction, understand what the instruction means, and execute it, run it. Those instructions are stored as binary data in your RAM because the RAM is fast. The problem with the RAM Yeah, we've discussed two limitations of RAM. It's very fast compared to a hard disk, but it's got limited capacity. It doesn't store as much. And when you switch the power off, everything in RAM is lost. It's volatile. But it's fast enough so that the CPU can fetch an instruction from RAM, put it inside the CPU, decode it inside the CPU, and execute it. And then it fetches the next instruction from RAM into the CPU, understands it, decodes it, and executes it, runs it. And it just goes round and round again. So fetch means get an instruction. Inside the CPU is a form of memory which is even smaller and even faster than RAM. So RAM, I don't know, the laptop I'm recording this on, it's got 8 gig of RAM. So that's 8 billion storage locations. Inside your CPU, you've got registers, and registers can only store an individual value. The RAM might store 8 billion individual values. A register would just store an individual one. So fetch means you get an instruction and you put it in the register. So the CPU says, can I have an instruction or can I have some data? The RAM says, yeah, there you go. There are 3 wires or 3 sets of wires that connect the CPU to the RAM. First of all, you've got an address bus. So that's saying, where is my instruction going to be fetched from? It's like if you order something from Amazon, Amazon can't just put it in a box and launch it from a catapult and hope it arrives on your porch. They have to put an address label on, and that address label tells you where it's going to be delivered to. It's exactly the same when you want to fetch an instruction. If you're playing a game, the CPU needs to know what's the next instruction of the game. So you send an address. You say at the start, I want the instruction at address 0. And then I want the instruction at the address 1. And I want the instruction at the address 2. I want the instruction at address 427. It doesn't have to be in sequential order. You can jump around all over the place, but you get different instructions. Those addresses go along the address bus. What's a bus? Well, think of a bus like something that gets you from home to school with lots of people on it. A bus gets lots of zeros and ones from one place to another. It's just lots of wires. Instead of drawing 32 different wires, you just draw one wire, and it's a bus that can carry 32 zeros and ones at once, or 8 zeros and ones at once, or 64 zeros and ones at once. Okay, so the RAM has received a value like 0 on the address bus, and that says, where am I going to get my instruction from? The RAM needs to reply and send the actual instruction to the CPU, and it doesn't send the instruction down the same bus. It sends it on a different bus. It's the data bus. It's the actual instruction or the actual value. One thing that's not shown here is there's another bus called the control bus, and that's where the CPU says, right, I've put the address on here. I'm going to send a signal down the control bus to say start reading. And then the RAM responds by putting the data it wants onto the data bus. So that's all fetch. Basically, can I have an instruction, please? Yeah, sure. Which one? This one. Okay, thanks. Here's your instruction. Decode. Decode just means the CPU works out what it needs to do. So the control unit decodes the instruction. So remember, the CPU doesn't understand instructions like stand up, sit down, add, subtract. It only understands zeros and ones. It's just made up of logic gates, and or not, X or NAND, all of those kind of things. It just has zeros and ones, ons and offs. So it has to look at the binary data for the instruction, like 000110, whatever, and decode it into meaning that means add this number to that number. So you look at the binary and work out what it does, and then you do it. The arithmetic logic unit performs the arithmetic or performs the logic comparison, like adding, like we did last half term, or shifting, moving across to the left or to the right, or one value and another, or one value or another, or not, or that kind of thing. And then once you've done execute, you just go back around to fetch, decode, execute, and that's all a CPU does. I'm not going to go through all of those because I think I've waffled for far too long already. Basically, I would like you to find P3 worksheets and work out where these things go. Now, it's rather irritating because this is all one picture, so you can't just write on it. So I'd recommend creating your own text boxes. Insert text box or insert shape is probably easier for you. Just draw another picture on top of it and then start writing. So you might have the input device of a keyboard over here, and you're probably going to have an output device of the display over here. And we've got to try and work out where all these different components are. I would recommend once you've put them on, you just delete them, and then you can do fill out the gaps. Basically, anything going in is on the left because we've got the arrows going in. An output device is going to be on the right, and a storage device is going to be under here. That'll narrow it down to get started. So we talked about a keyboard already. It's an input device. We've got another input device of a mouse. So I'm going to hold down Control, drag that across here, and put mouse in. And why are they input devices? Because they take data from the outside world and put data into the computer. So on the other side, we can have output devices, things that display things or show the result of the calculation out from the program into the real world. So a speaker is an output device that outputs sound, and we could have a display as well, like the screen. I want to move it so I can still see the arrows. There we go. Oops, display. Then we can talk about our storage devices. We've got two types of storage, primary storage and secondary storage. So the primary storage is going to be fast. Come on, it's not working. Hold down Control and drag a copy. There we go. The secondary storage is non-volatile, as in the stuff stored there will be safe when the power is off. But the primary storage is faster, but doesn't store as much and is volatile, as in when you switch the power off, it's all lost. It doesn't matter which way round you draw these. If you put mouse at the top, or if you put display at the top, or if you put hard disk on the left, it doesn't matter at all. So now we've got 1, 2, 3, 4 left. I'm going to pause the video and see if somebody can put them in the right order, and we'll work out what some of them are, because some of these we haven't talked about just yet. So we talked about the arithmetic logic unit. That's the weird shaped one. That's the one that looks like a V. I'm going to just say ALU. It's weird shaped because it's got two inputs at the top and one output. For example, if you want to add something, you need two inputs because you need to know what to add to what. So you often see it like that, V shape, two inputs and an output. The output from the arithmetic logic unit often goes into the accumulator, the general register. I'm going to put that word accumulator in there because you'll often see that. It just accumulates a value. Remember, a register stores a single value. Very fast, but doesn't store much at all. So for example, if you're adding 1 plus 3, the result, 4, will get stored in the accumulator. Just stores a single value. Okay, so we've got two left here. It doesn't matter which way around we have, but we've got two registers inside the control unit. Let's explain what both of them are. Come on, Word, don't be irritating. I'm just going to put PC for program counter. Remember we said if you send stuff out to RAM, you've got these three buses. You've got the control bus, which controls everything, obviously. It sends control signals to say start reading or start writing. You've got the address bus to say where you're reading from. Well, the program counter keeps track of where you're reading from. For example, when you start your code, you want to run the first line first. So you'll have a 0 in the program counter, and then you fetch, decode, execute from address 0. And then once you've fetched, decode, executed the first instruction, you increase the program counter so that it stores the address of the next instruction. So the program counter is going to store 1, and you fetch, decode, execute the instruction at address 1. And then the program counter increases to store a 2, and then you fetch, decode, execute the instruction at location 2. Basically, the program counter just keeps track of the address of the next instruction. And then the instruction register is the actual instruction that you are executing. So I haven't written out the full values, sorry, the full names, program counter and instruction register. Okay, so we've been working through activity 1 and activity 2, but I'm aware that your understanding might be a little bit fuzzy as to how the different buses work and what the registers do and everything like that. So I'm going to give you an opportunity to play around with this. Don't worry if not all of this makes sense at the moment. I'm going to play a little bit of a game. To begin with, we just want to have the idea of a sequence of instructions. So we've got a little tank that we have to control through a map. The idea is we can give a sequence of instructions and it will follow it. It's manual control at the moment. I'm going to press upwards 4 times, maybe again, and really dodgy graphics, 1, 2, 3, 4, but it should follow the instructions in a sequence. Not particularly helpful at the moment, but if you can do something manually, then you can control something and automate it, which is kind of part B here. Programmable computers allow you to automate simple tasks so that you can save money and save time. Why put a human inside a tank when you can get a tank to drive itself? It's cheaper and that person is less likely to get injured. So if you click on the tank, you can have these low-level instructions. Now, you've been writing Python so far. Python is a high-level language. That doesn't mean you're more intelligent if you can write it. It doesn't mean low level is easier, probably the opposite. Think of it like a high level is like a hawk flying in the sky, and low level is like an ant crawling on the floor. If you see a breadcrumb on the floor, the ant is going to see it in immense detail and going to take a lot of effort to get round it. A hawk is just going to probably not even see that speck of detail, that breadcrumb, because it's too high above. So high level means high level of abstraction. Abstraction means hiding unnecessary detail to focus on the most important thing. So high level language means we hide all of the things about how the processor works. We don't care about the registers. We don't really care about where stuff is in memory. We just write something like print. Oops, can't even spell print. Oh dear. Hello. That's a high level programming language instruction. You write a little and it does a lot. Low level instructions, you have to write a lot of code to do a small amount of stuff, but you've got complete control over every value in memory and exactly what's stored in the registers and complete control over the timing. So low-level code is going to be great for performance, for getting absolutely every bit of speed out of your code. Let's have a look and see what happens. So I'm going to step through this. I'm going to press step. The first instruction here, imp, well, we can have a look at the instruction set. Imp stands for input. We're going to read a value in and store it in the accumulator. So this fetch, decode, execute cycle, fetch means I'm going to fetch an instruction. What on earth is 901? We'll find out. From memory location 0. Well, why 0? Because you've got 3 registers. The program counter stores the address of the next instruction. So fetch means look at the program counter register, put that value on the address bus, send it to RAM, send a little signal to RAM on the control bus that says read from location 0. RAM says, oh, okay, location 0 stores 901. What is 901? Well, we don't care yet. We're on fetch, not decode. We just put 901 into the instruction register and say, okay, thanks, we've fetched. Then we step. We go on to the decode stage. So decode means look at that instruction, 901, and use your control unit to decode it. So 901 from our instruction set means 901 means read an input value from device 0, which is just the user, and store it in the accumulator. So we've fetched it, we've decoded it, now we're going to execute it. Okay, I'm going to put a number in, 63. That value is going to get stored somewhere when I press OK, and it's going to get stored in the accumulator. One other thing has changed. Did you spot what's happened? Look at these 3 register values. Good, yeah, the program counter went from 0 to 1. Why? Because the program counter always stores the address of the next instruction. If it stayed at 0, when we fetch again, we'll just fetch the same instruction, and we don't want that. We want to move through our code. So the next instruction is STA8. So we fetch it from location 1, we put it into the instruction register, we decode it, which means store. Store what? Store the thing in the accumulator. Store where? at address 8. So hopefully the value I typed in, 63, should now be stored at location 8. So at this point, you should be aware that in each of these locations are instructions. Can you see one instruction in low-level code is one value in memory? We might not know what 109 means until we decode it. How do we decode it? We look at the instruction set. What's the instruction set? It's just a list of what all of the binary means, a list of what all of the instructions are, what everything it does. But we're also storing some data. So in here, we're storing a value and we're storing another value. So this is the key part. Von Neumann processor architecture means you can store your program code, your instructions, and you can store your variables, your data, in the same place. That makes your processor incredibly flexible, because you might have a program with loads and loads of instructions, so you need lots of memory space for instructions. Like Photoshop is a complicated program, it's going to need lots of space to store all the instructions. Or you might have a program that's really simple in terms of code, but stores loads of variables, and you need lots of space to store your variables. In von Neumann processor architecture, which stores them both in the same place, you can do that, because you can store as much as you want of data or instructions shared anywhere in your RAM. Okay, so I'm not expecting you to understand the little man computer yet, but you can play around with it if you want. Once you finish the practice level, the manual control one, you can see the code to make the tank move forwards. So you can step through the instructions here, load forwards, send that to the output device, which will make the tank actually move, and you can put the instructions in to see if you can make it move. It's probably a bit more advanced than most of you can manage today. The most important thing is making sure that you've got the answers to activity 1 and activity 2. So do remember at the end of the lesson to save your Word document and then submit to half term 3 computers 1, please. If you're in the lesson, then you should save the Word document into your topic 3 folder, the computers folder, but it must be submitted to half term 3 computers 1.